you tried to listen did complaining about the audio quality. What we'll be doing the first lecture today is giving motivation and a little bit of context on research and following research data, talking a little bit about the so-called fourth paradigm in science, giving a little bit motivation and information on good scientific practice, talking about risk analysis, what is risking research data in general, particular, and talking about knowledge preservation. So this is all about, pretty much all about. Research data management, of course, is not without benefits, but challenges you will find as well. And we give you a little bit first guidance, so what you should do in your personal scientific practice. So that is the sum up of the take-home messages. So we will provide a broad, but in this lecture, yet a shallow overview on the topic. It's quite broad by now, so we will go into more detail in this introductory module, but in the other modules 5, 6, and 7 as well. So you will learn briefly about research data and research data management, and you will at least partially understand that we have different needs in the various disciplines. So depending on your field you are coming from, you are working in, there could be totally different methods, file formats, and so on you are dealing with. And we hope to motivate you that you look critically on your everyday business and check if your daily doings adhere to the principles of the good scientific practice. Research. Research is around for quite a while, so it's not a new thing. We have to deal here. And it is producing some results, some artifacts all the time. The information we create from our research practice could be represented in various forms, so scholarly writing, and of course collected specimen, collected stones, whatever, depending on your field. All this is happening for quite a long time. The idea behind all this is that information you got from all this is to be made durable, because you want to transport that information through time, and you want to share this information with your scholarly colleagues or with the whole society. Typically, no one is acting just out of his own and gets to some secluded office and thinks about stuff for many, many years, and in the end publishes a brilliant book on things which no one has seen in before. But typically, research is about prior work and building up on prior work. To actually do that, you are reusing or repurposing the stuff which other did in before. The artifacts could be, and especially are, in nowadays, is data, is code, is interpretation of that stuff, are digitized objects, and all the other objects I was talking about before. It is to be kept in a transportable or reusable way for allowing scientific advance, and of course to prevent forgery and being able to verify results of others. Unverified results pretty much would end up in fake science. So if no one can actually check what you did, it's pretty much as if you never did that. Research data, depending on your field of science, so I will repeat me pretty often in here, everything is rather field specific, could take whatever forms you might imagine. So it could be simple spreadsheets with columns of data. It could be some proprietary file formats falling out of some sensors. That would be all kinds of text files in various formats. That could be communication taking place in social networks. It could be survey data, so on and so on. It could be visualization, simulation data, pretty much every thing produced in the course of your research is research data. When you try to define research data, you can say that it is kind of collected, observed, or created for the purposes of analysis to produce and validate original research results. So if anyone tries to replicate what you did, the person most probably would need the primary data you were dealing with. That is both true for analog and digital materials. All this is input or was input to your science. Lab notebooks, software as well could be classified as data depending on where you are working in. That data can be just entirely stem from the digital world, so then you often find the term born digital, or it could be converted to digital forms, then being digitized. Could be scans of books, 3D scans of any object, or digital microscopy, whatever, to transform analog material to digital ones. And again, depending on the type of field or subject you are in, you will have different types of research data. The natural sciences typically, or much data is coming from some instruments, from measurements, experimental observations of in a broad sense, sensor inputs, telescope, microscopes, imaging, whatever you might use. But it could be sketches, depending on which field you are in, diaries, lab notebooks as well. In the humanities, the focus often is quite different. It might look much less technical, but you might have still images, so photographs, video, and audio you are working with. Often you will deal with text, documents, spreadsheets. Maybe you try to organize your data in a database, or dealing with sketches as well. In economy, psychology, that is just random examples here. You might as well deal with text documents, being of other formats, being of other types, huge spreadsheets or quantitative data you gathered from, for instance, household survey data. Survey results or interviews in general, or interviews transcripts, could be both in the form of recorded video or transcripts of it. When you go to engineering, it could be simulation data or models and software which are relevant in here. Biology, again, photos, artifacts of any specimens, samples, lab notebooks. Yeah, and just insert your field here and think about what I might have missed in my summary. So what we see in here is, just coming back to the very introduction, is, so if you actually want to talk about what you are doing, and you might feel that it is more easy to talk to your colleagues than to outsiders, that is because there are often common community-specific standards which exist and which kind of formalize that exchange of ideas and knowledge. With all of this, there comes discipline-specific metadata, data describing your primary data, and many of you will not necessarily share the same technical environment your software is running on. It could be totally different of you using a laptop or a tablet. Others might use a big HPC, high-performance computer, or server and cloud resources to run particular kinds of software on totally different underlying operating systems or software bases. The fourth paradigm, that is the guy who pretty much came up with that idea. He's dead by now, but the book is really often cited. Just look it up in Google Scholar, and you will pretty much find it as a first hit in the search index. And he tried to describe what is pretty much happening today and where we are heading for. So talking about empirical science, so kind of, but yeah, it pretty much depends on in which field you are, starting more than 1,000 years ago, where you find mostly description of observed phenomena. That could be all kinds, so what you see, what you smell, whatever, and that is yeah, kind of seen as the beginning. Much younger is the shift towards theoretical science, where you do model building and try to generalize what you have seen, what you have observed. Pretty young is the computational science, so computers being around much longer than 20 years, but became such ubiquitous that pretty much every field in science is using them, for instance, for the simulation of complex phenomena, or to reduce the number of expensive experiments. So it could be either, for instance, experiments with animals, when you can simulate certain substances you produce in chemistry or pharmaceutical research, or on the other hand side in industry, it could be much faster and easier to just virtually crash your car and check on your security mechanisms than doing it all the time in the actual world. Now, and that is the fourth step the guy was talking about, that is data-intensive science, which is connecting theory, experiment, and simulation, and dealing with huge amounts of data from sensors and data produced by simulations, all the data processing happening in software, and we typically find that the data is somewhere stored in networked infrastructures. And what is happening, that we gain new kind of knowledge by analyzing the integrated data, meaning bringing data in from different fields and different sources. You find it by now described by words like e-science, data-driven science, data-intensive science, data-intensive computing, stuff like that. In the middle is data, which is the kind of the key enabler. So the idea is just to keep and never throw away any data like the big data giants in the industry are doing, hopefully to gain new kinds of knowledge from it. But just preserving the data enough, that will be discussed throughout this lecture and course. The big hype is, and the big hype is happening at the moment, that you try to find new relations of things, try to find intelligence, you will find only what your algorithms are looking for. So there's still, and that is a good message on the other side, the human brain required to define a proper experiment or a proper data search setup to actually gain new insights. There are a couple of nice examples in here. Social graph theory is one of those. Locating of old friends was or could profit from the customers who prefer X, also like a Y thing. People who know A also know B. Other problems might come in here, so where you might go much too fast with your conclusions. So if you say if B is a terrorist, is A also one. Find strange facts. There are a couple of nice, half funny, half interesting examples around. So that the Italians located 18 CIA agents in 2006 on, I think it was partially Facebook and other data, where there were 18 mobile phones only, which only called each other, but no one else. So being a circle which do not have any connections somewhere else. And interestingly, that those accounts had consecutive credit card numbers, so they were just generated in a sequence. So, of course, they learn from it. So, in the future, most probably, they will be more clever on how to handle that. Another great example is that Strava running app thing, which is or was quite popular among US soldiers. And the idea is so to challenge yourself or improve your runs or just show how great you are, that you can share those tracks. And many popular tracks, so you see it for parks, cool scenery outside or whatever, are made public. Often people who handle such an app do not know how to properly set all the settings in it. And so if you are looking for popular tracks in the middle of nowhere, most probably those are military camps, especially if they are located in specific regions like Pakistan or Afghanistan or whatever. And then you see in otherwise kind of blurred, grayed out maps that you find such structures like that, and often even get an idea on the size and layout of the compound, because soldiers pretty much were running, following the edges, following the walls, either inside or outside of their camps. More serious examples are found in other fields, for instance, medicine, find new pharmaceuticals. So the classical way trying to find a new drug are pretty much getting to their limits. And especially in cancer treatment, there is improvement on the way. So chemotherapy is a pretty dangerous thing to do, and you do it on a last resort to kill that cancer. But not every kind of cancer is kind of responding to every kind of stuff which is around. And sometimes one drug doesn't work at all, but another drug is working very well, which was not understood in before, but was large data analysis and learning from good cases. The chances are rather high that we do not need to try out different drugs on that patient, which is usually already weakened by the cancer, but can start with the right one just from the beginning. Data-intensive science just means very often that we reuse existing, or pretty much means reusing existing data, which once was expensive to create, that might offer insights to new research, insights to new findings no one originally thought about when the data got created in the beginning. There's, for instance, an example from the forestry department in Freiburg. A researcher is doing those tree cuts like visible over there for more than 30 years. And originally, they were looking for totally different information on it. But by now, more and more researchers on climate change are interested in that data, because you can see very well from the thickness of those rings on it how the climate changed by changed environmental conditions, for instance, in the Black Forest, and that those trees are growing much faster every year, and the growth period is longer than it was in before. So the re-evaluation of that old data and recombination of that data sets might give you another nice examples, like trying to pinpoint your findings to geographical locations on Google Earth and see another set, or might learn another set of patterns from it. Yeah, but having all that data around, and we would like to see it preserved not only in the meaning that we have it somewhere, but that we can make use of it. Where's the actual problem? So collecting the data most probably is done, but when it's about describing the data, because you need to put the data into context, otherwise you might not be able to train your artificial intelligence to make any useful findings out of it. This is often a missing piece. Same on curation of the data. So that when you deal with the data to learn which part of the data or which data sets are relevant and which data sets, for instance, could be easily reproduced by running a tool on it, and thus do not need to be stored in the long term. Because too much data might be a kind of spamming, as you know from the email, so that you kind of might miss important information because there's simply too much data on your drive around. What is the challenge in digital preservation? It's just storage and backup, or is there anything else? So if we look on the different levels which is involved to actually make use of the data, you see that we have to deal on some physical, logical, and then semantic or intellectual level on it. We will see or discuss this a little bit later on. When all is about data and the reuse of data, then of course we need to think about means on how that data could be made available. So typically what we do find by now is that just the final results, and often in an often very condensed and boiled down form, is happening. So in the end, you might start with a huge data set and come up with a journal article being just about 6 pages long. So and from that information, it is often not entirely clear what all the original data was, and how to deal with that data. So that data should play a much more important role and will hopefully lead in the future to a way of organized publication of that research data. We might find some hybrid forms already. So some journals, for instance, require that you link your data to the publication, so that if anyone is interested in replicating or in reusing the data or repurposing the data, that becomes more and more possible in a way like that. But that link, of course, needs to be kept stable for quite a while, so that it's not only possible after just after the publication got published, but for a number of years beyond that point. There's a rather popular example. Just because of the big issue of climate change, the Pangea is a platform trying to provide a means for publishing geoscientific and environmental data in a way that you can actually search for it. So if you look at the research data pyramid in a way, so the publications which actually link data to it, the number is still pretty small, and then there are a couple of more things you want to see around. That you not only have the boiled down condensed version of the data sets, but are able to work on the raw data and primary data sets to see all the data which maybe got sorted out or was not used in that particular publication, but could be of yours for your purposes. Those figures are a little bit older, so 2011. Often the data is simply getting too big that you actually can put all of it just on some hard disks or USB disks, but we still see it in many professorships in Freiburg as well, that old projects are simply kept on external hard drives put onto some shelf, and thus being out of reach of pretty much every other person. So what is research data management? It's pretty much that we have to curate research data throughout its entire life cycle. So in the beginning, when we do some selections, when we run codes or applications on it, produce intermediary forms and so on. What we would like to achieve is that we are allowing reliable verification of the results, and of course permitting new and innovative research coming out of the data, which we might not have thought about when we designed our experiment, our research in the beginning. A little bit about risk analysis to give a short overview on what we are dealing with. Digital preservation is the term on dealing with the accessibility over long periods in time, and we have several layers to look at. It's the physical layer at the beginning, so somehow the data, the information is getting encoded on some medium. Technological considerations above of that, and then of course the intellectual and semantical threats to it, because the meaning or the understanding might change over time on how to read or how to actually read certain data sets. In the physical world, pretty much everything is decaying in one form or another. Same is true for pretty much every storage medium, especially the removable, because often uncovered types and thus often unprotected types of mediums. The once popular mediums like CD-ROM, DVD, or Blu-ray, we already have seen it in our experiments, and we did at our professorship in the last couple of years that with increasing the density for optical storage medium, we see an increase in the risks on it. So even brand new DVDs you just wrote in your DVD burner, depending on the quality of both the device and the medium you bought, that they do not really last for very long. And there was another issue which occurred in a certain generation, that there were certain bacteria around which were eating up the glue layer, which was, yes, some biological glue, which they liked to consume. And the information on that particular disk, even if it was a commercially created and pressed one, was lost. CDs could last for quite a while if you do not expose, for instance, the back layer of it to direct sunshine, or keep it in a mechanically unfavorable position so that it gets out of form, and if it's spun up in high speed, that it simply breaks down to shards, and you cannot do any more on it. So Blu-ray didn't get that much, or isn't used that much for storing data in large quantities. It is mostly handled by external hard disks by now. So it could be seen as a little bit less problematic with hard drives, because they are well covered, and so the medium itself is not that much exposed to external threats. But of course, if you drop a mechanical disk, it easily could break, or if it's getting old, the motor or the reading heads could get easily out of sync, so that you cannot read your data from it either. That was pretty much on the lowest layer, but if you look on other layers as well, if we see the deprecation of connectors and standards, so if you are not around for a while like me, then you most obviously won't know about the MFM disk controller. Same is for other standards. Even for computer standards like SCSI being around for quite a while, they are compatible to a certain degree just on some logical layer, but there's no chance to connect some 20 years old, and 20 years is not a long period in time, to the modern SCSI whatever 320 controllers, which was one of the latest parallel standards, and the serial attached SCSI disks of today. Same for the IDE to SATA controller switch over, where on the technical layer, on the command layer, not great changes happened, but the physical connections were not the same anymore. What we did once to trying to read disks from the beginning of the 1990s in a machine which was from the end of the 2000s, so manufactured maybe in 2007 or 2008, and even if everything was fine on the mechanical electrical layer, we got strange results when reading those disks because the timings were different, and no kernel and no controller actually told us that we were not reading the proper data from the disks. It took quite a while to find it out because the image we created, just reading the entire disk bit by bit and put it into a file and trying to open that file in a virtual machine. There will be more about that in other modules. We experienced strange behaviors of that virtual machine until we started to check if the image was being faulty. And if you looked into the image, we saw that there were mixed up or different bit patterns, even read from the same disk. So we started to do checksumming and saw that on certain controllers, every disk read produced different data read from that disk. And typically, that is absolutely non-obvious to you, and so no chance to actually detect that something went wrong here. In general, there's not a good, or I cannot really give a recommendation on simple storage media you should use at home, because in general all digital storage media are unreliable. So every physical storage medium becomes obsolete at some point. Even if it's possible to read optical media of older kinds like CD and DVDs in today's Blu-ray players, but no one is guaranteeing you that those readers will be around forever and being able to easily attach to the computers of the futures. So for storage strategies, if you look at best practices given out up to now, where no centralized or general offer, for instance, by the university research institution exists, was at least two different forms of storage in two different locations. Of course, you should try, if possible, to maintain the original copy, because successive copies could end you up with altered files without the chance to you to actually see what happened and in which step, and on how much you need to go back. And depending on if you are in the physical world, the recommendations were at least that you should copy over your data to a new medium every 2 to 5 years, so to kind of keep in pace with the technological change. Of course, it would be possible that you easily can attach an even 15 years old flash drive still to your computer, but something other might have happened to that device in the meantime, so you should at least try to do it earlier, but you can of course keep it as an original copy and hope that you have a chance to get back to it if something else failed in that row. Some more of those older best practices. So for the future, with proper research data management, we will talk about other means to deal with it, and especially tackle the higher layer problems we will see. Data integrity checks all the time are a good idea. So creating checksums from your files, so to see if something got altered when you just copied files over the net, for instance. If you're actually using some backup systems, it is often a good idea to test the file recovery. There are many backup systems around, but if you're not an expert on actually using them, so you might misconfigure them, and if it's actually required that you go back to a copy, then you should be or you should be able to rely your work you did in before. And what to protect, of course, not only the data, but there's much more about it. There, on a more higher level, above the actual physical storage medium, number of technological risks to it. So if you think of having your bit stream, meaning your file of whatever type, successfully recovered, it does not mean that you actually can make use of it. That is because of the fast technological change, which pretty much changes the scientific work desk, the combination of hardware and software as well. So you might find that the hardware architecture changed. Just think of the Macintosh platform undergoing different changes in the last decades, or the switch over from 32-bit PC architecture to the now prevalent 64 bits. Different operating systems are getting updated all the time, especially because of new features which should get added, or just security reasons. And if you look at some older file formats, the typical example would be asking your parents for the original copy, if they did it electronically, of their PhD, master's, or whatever thesis. They might have done it in some old version of a text processor, which all produce different file formats, and those file formats or files typically named all .doc for document, and without context to it, no chance to actually read the content and make sense of what they created in there, and even if it's just 30 years ago. Think of books, think of subjects around which typically last, and you expect things to last much longer. And there are other issues which got found out in the last couple of years. That is that the technical platform where everything is happening on, so the computer, the software stack on top of it, might have severe impact on the results you get from your data. So what people have seen, and it got published, that is the graphical output, the visualization of a quite common program in medicine, which is actually even open source. It's a beer server, whatever name, didn't have it put here, unfortunately, but nevertheless, what was happening there, or what people found out, that is a program which reads from CT scans of patients, and doctors might derive the situation of that patient from it. And depending on the underlying hardware platform, the underlying operating system, actually the results were quite different, especially those corner cases where in one setup, the patient could have been classified as being ill, and in other cases not, because being lying rather near to the edges of that internal decision making. That all was dependent on both the hardware architecture, so different results when the same software was run on 32-bit and 64-bit, and different results if run on top of different operating systems like Mac OS or Windows, or different results in different versions just because of different use of the mass libraries and rounding errors and so on. And that is really a severe thing. So it pretty much depended on where you did go and what kind of technical environment that particular doctor was using. That one had a significant influence on the same reading of your state and a significant influence on the recommendation that guy might have given to you. Another example is just from my sister's experience using the quite popular SPSS statistical software suite, doing surveys on for empirical research, doing it on within different countries, and more data is getting added to the pool. Same methodology, but more countries added to that survey. So data or results being just 4 years old were not being able to get reproduced in a more modern version of the software. No one was actually understanding it in the beginning. So the computer environment got regularly updated, and so they got two major updates of the SPSS, resulting in that pretty much everything was right on the right side of the on the left side of the comma, and everything on the right side of the comma different, which is really a disaster for research, because by then it was not actually been possible to prove the research they did in before, but to understand what the actual problem was. So they had to find a proper machine or a proper technical environment where they got the version on it, checking on the data, and saw, okay, the data is actually the same as it was in the publication. But by now, for their work, it's quite problematic. Sample research data, because there are changes in contextual knowledge. So if you have missing or incomplete documentation, then it could be quite tedious to find what a certain data set or a certain column in a table or whatever wanted to tell you. There are ambiguous data formats and descriptions, so it might mean different things to different persons when they try to understand this, and they are changes in terminology, units, and basic assumptions. For instance, in mining and metallurgical research, so when getting back to the medieval ages and you wanted to try to find out what were the results of mining of different mines spread over Europe, for instance, then it was quite problematic trying to compare the results of different mines to each other, because they kind of using a unit of the same name, but that unit in the same name could be different to another by the factor of 2 and above. And at some point, the French, for instance, started to standardize things like the meter or the kilogram and so on, and to be kept in mind, so that in the meantime, there could be a change in understanding of the data you have in. Organized, which might be different, quite different across disciplines. So if in one discipline you have a typical ordering of things, that could be seen or that could be lost, that information, to others not being from that discipline, and so important contextual information on data interpretation might be lost. Human errors will get in every time, and we have all the technical issues, machine breakdowns, and so on. What we got a couple of years ago in Freiburg was a near catastrophe in our computer center, just because of an extremely hot summer day, where we got an unplanned shutdown of a couple of servers, which did not recover all when being powered up. So even the combination of those factors might risk your data as well. Catastrophes are same thing, just on the larger scale, and you will find security flaws as forgery of data, sabotage or becoming more relevant threats by now. If looking at universities from that's more the organizational perspective, you often see a couple of risks which are particular to them. So we have understaffed, underqualified maintenance crews, because the pay in the public sector is often less than in industry, not necessarily attracting the best people for that job. Underfinanced IT departments, missing rights management, so that you not properly handle on how should or who is able to access a particular data set, because no one really thought about authorization and the missing know-how thing. So all those risks, of course, should go somehow into your consideration when you think about preserving research data. Forgery of research data is getting quite a or got some audience in the last couple of years. It has a long tradition, so it is done for whatever economical, political, or criminal reasons, and it is not really unusual in the scientific domain, because you have all you experience, time, staff, financial, whatever restrictions. And if you can cheat and by gain better results or higher regards or whatever, at least for a while, it could be attractive to do so. So you find all the different examples from different fields like biology, biochemistry, and so on. When people actually started to doubt the results those particular guys created, they usually were unable to present the data and lab diaries, which everyone would expect to be around for reproduction. It could be or could get rather nasty. So if we are dealing with a Nobel Prize candidate, yeah, fortunately they found out before, so that the results the guy published were not were unable to reproduce. In Germany, the Max Planck Society and the German Science Foundation started to require it. It's a couple of years ago, I think it was more than 15 years, that the primary research data, lab diaries, and so on should be kept for 10 years after publication. Of course, those 10 years are disputable, are kind of an artificial time frame, but you have to define it at some point and then find out if it makes sense or not. And it pretty much depends, of course, again on the discipline you are in, because sometimes it actually makes sense to keep it even longer or sometimes less. We should define at least a little bit thing when a little bit of stuff when talking about research data management. So preservation as preserving, keeping access, keeping data available around, that it has more meanings than we might just primarily think about. So preservation often has a managerial function built into it, and is not primarily about conservation or restoration of items or the storage media or backup regimes. So on how you organize it, or on how you refresh your tapes, if anyone would do things like that. So digital information is different. Technical problems with ensuring the continued access exist, as we have discussed. But here and again, we have to plan well in advance, because we have to allocate resources to do all of this. By now, we find often the phrase of curation, which is the concept that you actively deal with your data and start to define what data sets, for instance, should be kept, or what data sets could be thrown away because it's just some intermediary results which easily could be, or for a moderate price, could get replicated from the original data you kept. A little bit confusing again is the term or terminology of archiving and archives, because archives in the traditional sense are around for quite a while. So it is well understood and discussed term in the archives and record keeping professions, but again, here terminology could be quite different to the different fields of science you are dealing it, so that you will find that you informally refer to any collection of digital stuff, because archiving meant for a long time, for instance, to create a tar or a zip archive from a collection of files. To formalize the handling of research data and dealing with it, the so-called research data lifecycle got defined or invented, or however you would like to put it, which is a model for creation, processing, use, and reuse of research data. As it is a ring, you have no particular end or so the creation of data does not necessarily means to sit on the beginning of it. It could be as well some reusing of old data sets and then sampling some other data from it, and then start your processing and analyzing iterations. Usually that is a repeated process, so you learn on how to properly handle it, or you redo it with new data sets and so on, so that you might almost probably will spend quite a while in that part of the life cycle. At the end, when you're coming to the end of your PhD, your project, or whatever, the data should get, or the relevant data should get preserved at some point, so that it can be accessed later on by others, coming back to the beginning of the lecture, that it can get reused again, so that you hopefully can create some new knowledge out of it. Reuse is a big hope, so that the old data could be input to new research, and hopefully generates new insights as well. In the end, research data management is a multifaceted challenge. That's why we are dealing with it not only today, but have allocated a whole summer school on it. So 7 modules and 3 weeks for it. So we have the technical level, which is not only comprised of simply the storage on it. We have the organizational level where we might find tasks like curation of the data. I just, I don't have it, but, sorry? The magic number is 5610. Hopefully everyone got it. So then we have additional levels if we do a holistic approach to it. We need to look at that is the financing, where is the money coming from, to keep up the different technical systems, to keep the staff required to do ongoing research, development, and of course to do all the training which is required to tell people on how to deal with their research data, on advise, for instance, on advising them then when they try to formulate applications for grants by funding institutions and so on. Typically, it involves quite a number of people and quite a number of technical and other systems in it. Then we have the stakeholders and their different perspectives. So we have the researchers. For researchers, in the beginning, it's not necessarily entirely clear, because somehow they got their data, or they create the data by their own, not necessarily thinking about all the implications you find with data management. Then we have the grant providers, which could be the universities, the states, or various grant provisioning institutions, like in Germany, the German Science Fund, the Volkswagen Foundation, giving money for research, and they have expectations as well. For instance, in the US, it is required that every publicly funded research, for instance, by the National Health Service, needs to be being open and accessible by others, because there is the understanding, if it's paid by the public, the general public should be able to profit from. Another perspective, of course, is the perspective of the system operators, which is a little bit of my perspective in that game. As being at the computer center, we have, or we should provide in the future, some kind of a research data management system. So we have to talk to a couple of people, not only the researchers, but financial departments and so on, to keep all this up and running and updated and well staffed, so that we can fulfill the processes we might give with that research data management. And of course, the society, which has expectations on science. We have seen quite some discussion coming up with the new president of the US, fake science, fake news, and so on. So to put it into a somehow catchy phrase and formalize all this a little bit, the FAIR principles were made up. That is a couple of requirements towards digital research data defined by quite a number of major institutions, which translates to findable, accessible, interoperable, and reusable. All those terms you find here, needs a little bit more interpretation and definition to end up with some proper research data management strategy in the end. All this is meant to support knowledge discovery, innovation, support data and knowledge integration, and promote the sharing and reuse of data. Here we are pretty much at the beginning, often because of a lack on understanding on the researcher side and on missing the systems which could provide the technical base to it. All this is to be meant discipline independent and allow for the difference in all those various disciplines dealing with digital data. A little bit more on the on maybe yours perspective of why you should deal with that, or why you should at least being aware of those concepts, and what are the incentives to safeguard the research results for the future. That could be on your reputation just by allowing the reproduction of the research data, and that is often only possible if pretty much everything which was the input to your research, the concepts and ideas, is well described and all being accessible. The validation definitely needs the original data used in all the processes you might have come up with. Visibility is a new is a kind of newish concept, not so new. Of course, pretty much the same you had with your publications. It might help you to enhance your visibility as a scholar in your field. So whatever giving you better page ranks, enhance the citability of your primary data, and fulfill open access requirements could fall or could be seen in that category. And there's the money side to it. So to push all those concepts well ahead, more and more financing or funding institutions are pushing a certain research data management agenda by requiring, for instance, that you have to come up with data management plans. Data management plans pretty much about organizing your upcoming research, so you do it in front of, not after you did your particular research topic, and put it into your grant application. That is an important part, and should be an important part of your future research, and is getting more and more important for researchers in general. That's why there will be another lection just allotted for that purpose, to talk about data management plans and what need to be considered within them. Yeah, that is hopefully what we get out from it. So long-term preservation and access, and in the end that it's more complicated and that the results are more trustful and reliable we get out of the research which is happening. Yeah, that is what we would like to achieve by this summer school. So to learn on how all this is working together conceptually, so that archiving is not necessarily the start of it, but usually you have much more activities you are doing which should take place before that actual maybe last step in a particular project is done, when handing, for instance, handing over your data to a repository for publication, or because some journal is requiring it that you put the data reliable somewhere online. Typically, it's quite expensive and often not happening if you push all this into the period of shutting down your project or handing in your thesis, because there's quite a bit of work going in to all of this. So you should plan well ahead to properly deal with that and properly adhere to those principles. There are, of course, benefits involved, so repeated again and again, but that data or your data might be a very valuable resource for others, and you already might have profited from the data taken over by others for your particular research questions, and should kind of give back those favors to the people coming after you. And allowing or adhering to the general concept of science, that you produce something which is valuable for the generations to come. Sharing of data, which is a kind of a new concept to explicitly do it, allows or facilitates new scientific inquiry, avoids duplicate data collection. So if someone sees that particular data set is already online somewhere, the number of copies could get well reduced, and that data as well, and that is relevant especially for universities, might provide rich real-life resources to train students on certain scientific workflows. What we should see with published data is that the credits of the data creator should be published or should be put there as well, because quite some intellectual might have gone into that. It as well can help you to support the evidence of your impact, and yeah, in the end, it is something to be proud of. So if you created an attractive data set which reused by lots of people, it would definitely add to your reputation, as well as it did for journal articles, well-cited journal articles in before. We talked about that already, not necessarily only the raw data is worth to preserve, but some intermediary forms as well. It is often dependent on how those forms were created. So if you run some very expensive, for instance, HPC processes involving lots of machine power on it to produce certain results, then of course it should be kept as well. There are other perspectives to it. Those perspectives my colleague Klaus will talk about later on, that complex scientific workflows needs to be preserved as well. So putting out the data only and maybe the publication to it might not being enough to get an authentic verification and reproduction from it. So what we might find to deal with as well for reproducibility is that we preserve the complete environment or single multi systems for it, pretty much depending on what in your research workflows. Just getting back to the example of my systems problems with the technical environments, it was good that they found at some point a laptop which did not get updated because it was out of use for some hardware reasons. Some keys didn't working properly anymore, so you had to operate it with a external keyboard attached to it, but that actually preserved that particular workflow they were using, and were able to get behind the problems they were experiencing with the different results from the same data sets. And of course, it might require that you need to cope with external dependencies. Usually, or depending on the field of science you are in, data sets are so huge that you cannot necessarily store them in entirety on your local hard disk, or you involve much more machines than just your single laptop, just because of sheer compute power you need, or because of certain processes you attach to your or apply on your data in a succession, which might run on different systems and in different environments. Then data needs to be handed from system to system, and that needs to be taken care of as well. That just as a lookout for what is to come later on in the second session to follow. There are those hardware and software dependencies. That is, just to sum up here again, particular configurations of hardware and software you should keep in mind. That is, somehow the heart of our digital preservation problem in here, because we already experienced and have seen the relatively short cycles of obsolescence. So especially in consumer hardware and consumer products, you see rather fast life cycles, which not necessarily would be required for the things you do, but which the computer and software vendors find necessary to push out new versions and to require people to buy new stuff. Yeah. Hopefully there's a possibility on reproduction, so that of course as well is taken from some other presentation as well, but I liked it very much. As given examples, the results might vary, and the variation of it might have severe implications, like given in the example for that patient's data analyzing tool in medicine. To understand the problem better, a couple of surveys were done in different states and different areas. So a couple of initiatives were doing it in throughout Europe and the US, demonstrating that there's a rather high interest in the long-term accessibility of research data, but in many fields, no concrete activities. That is a typical mismatch you will find in many disciplines. The primary responsibility for the data is often by the scientific personnel. So if you are working for a project, you are the person being responsible for the data pretty often on the entire stack. Of course, you should have a good understanding and a good idea, at least on the intellectual level, on dealing with your data and having your tools, environments well chosen. But often you have to deal with all the measures of keeping backup copies, updating backup copies, keeping the data around, and no one is actually helping you with that. And often the knowledge on policies on how to proceed, on how to do it in a proper way is rather low. So it's not that long ago that we have seen in grant applications for data management. In those days, it not necessarily was required in such a formal form that researchers in natural sciences actually suggested to burn all the data and results on CDs or DVDs and then put them onto shelves. And that, of course, today would severely risk their chances to get actually their research actually funded. And in all those different disciplines, we find lots of heterogeneous, often proprietary formats, because for long times no one actually thought about that problem properly. Same, of course, applies to software. Lots of different, often commercial, black box-like software being in use, like that aforementioned SPSS example, which risks the results of your research you did or deviated. When looking on the deficits in that domain, the typical answers you find, especially in research, is no time for it. It's not directly research related. So why dealing too much with those issues? I cannot publish a paper on that, and it does not really help me in getting my PhD finished or whatever, and often no incentives. So that is the bar in that field is raised by the funding institutions, and of course by hopefully seeing more publication of raw research data in the future. By now, in many disciplines, it is rather or for many scientists, especially in the humanities, in the traditional fields, it's a kind of a scaring thing because they hope to keep their data private as long as possible and to squeeze out every bit of information they have an idea to get from the data before allowing anyone to actually look at it. And of course, missing infrastructure to do it in a halfway optimal field. Coming to an end of that session, a little bit recap on research data management, digital tools and workflows driven by fast technological change and scientific advance. So we see obsolescence of machines, data formats, tools, which is a phenomenon visible in the digital domain quite from the beginning. We see lost data not just resulting because of decayed media, but on the threats on all the other levels as well, including human errors, security breaches, and so on. The good scientific practice as got established over the years in all the different disciplines, on all the different scientific methods in use, is to be established in the digital domain as well, where research data management is coming in at that point and becoming much more relevant in the future. So it could be, or research data could be the future asset of every university and research institution, could become more relevant because it is adding to the reputation of the scholars involved to it, and we have to deal with a couple of challenges. So when we look at it, not every scientific domain is starting from scratch, but they already started to deal with the problem somehow. So we have a number of pre-existing solutions which get or which needed to get properly included, referenced, and handled. So no one is getting convinced if they need to do things totally different as they did it on before. Cooperation of scientists and institutions should be kept in mind. Data sharing, that is part of that problem group. And we have all those very diverse requirements from the various domains. Thank you very much for your attention. And just in the end, a little bit of advertisement of things to come. So there will be computer science PhD colloquium tomorrow in the evening. That is a research seminar where two of the EAD lecturers will present on their ongoing research. It will be Klaus and Christopher tomorrow in the evening with the topics given in here. All this is not mandatory for you, but it's open to you to come. It is held at the C3SL Auditorio da Informatica on the other campus, and we hope to start at 6 p.m. sharp. That auditorium is much smaller than this one, even a little bit less nice than that one, but nevertheless, limited seats. First come, first served is the formula here. The outlook, what is to be expected now, my colleague starting with his module as well, And the next two lectures will follow then on Thursday, 14th of March in the module 4. Me presenting on the researcher's perspective and practical challenges, and Klaus presenting on in the track on abstraction of computer systems, emulation and virtualization, different but intrinsically linked. Thank you very much.
Ideally, we have such what we call a trap condition. So we have the guest operating system. The guest operating system wants to thinks it runs on real hardware, and it wants to execute a privileged operation. Then we get a notification from the CPU. The operating system or the virtual machine monitor is notified and will handle that situation, emulates, or jumps here into a special routine, emulating this privileged operation for the guest system. It will be a bit slower than executed on real hardware, but the guest system won't notice at all. And then it will return the control to the original context, so the guest operating system will continue to function as normally. But some instruction set architectures are very, very difficult to virtualize, because it's kind of difficult to detect or isolate instructions that need to be specifically handled. So we need a formal definition what needs to be trapped and what needs to be handled specifically. So the Popek and Goldberg already 74 derived sufficient conditions under which an ISA supports efficient support of virtual machine. And so they used very old machines like IBM System 370, the very famous mainframe, some other mainframe machines, but very interesting, it still holds for computer systems today. Let's continue with privileged instruction is an instruction that must trap if the machine is in user mode and must not trap if the system is in if the machine is in system mode. There were some famous examples, and why is this important? Because a privileged instruction typically changes the physical state of the machine. So it's like it switches a flip, it flips a switch, or it presses a button, and this button stays that way after this instruction has been done. So if you think back to the isomorphism, so we have two virtual machines running on the top of the physical hardware. One presses the button, one does not press the button. The one that didn't press the button still thinks the button has to be pressed, or is not, or is in a not pressed state. So the hardware is in a different state. But if one virtual machine is able to switch something on the physical hardware, the other virtual machine will be confused. So if it tries to do the same, or if it checks the state, the state will be different than a few milliseconds before when it has been when it checked previously. So this must not happen. Privileged instructions are typically, or can only be run in system mode. Non-privileged instructions can also be are run in the user mode. However, to make things a bit more complicated, we have something like sensitivity. There are instructions that interact with hardware, but actually the system designers allowed it to be run in user space, user instruction, because they didn't anticipate it, the case that they wanted to virtualize this. So to make this a bit more plastic, so we have the whole instruction set. Most of the instruction set is non-privileged. Then we have a subset which is privileged, and we have a subset which is sensitive. And so what we then need is not only to trap on system or on privileged instructions, but we also need to trap always all sensitive instructions. Because the behaviors, for instance, the control sensitive instructions change the configuration of some resources, or the behavior sensitive instructions depend on the state of a and then the Popek and Goldberg introduced the term innocuous. So even instruction is neither control nor behavior sensitive, which means all innocuous instructions must be natively executed. That's very important for it. So we don't want to emulate. Don't want to handle them in software because that's unnecessary. We want to control. We want to have the control over resource. So we want to make it impossible for guests to directly change system configuration, and we need to guarantee equivalence, which is very important. So that we have always the identical behavior, the virtual machine run on the which we will discuss also in the next session. Is very difficult to prove. Very difficult. So this is the summary of what I just told, but important are the pictures. So if the sensitive instructions are not a pure subset of the privileged ones, it's not possible to implement an efficient virtual machine. If here the sensitive instructions are proper subsets of the privileged instructions, it's very easy to efficient virtual machine. So this is an example how this actually works. So we have the guest code. It runs a it runs the whole guest machine runs in user mode. A privileged instruction causes a trap. The trap is caught by the virtual machine monitor. It dispatches some extra code, so run some special code handling this session, and after that we jump back to the next instruction, which follows the trap one. So what are the problematic instructions? Sensitive instructions that are not privileged. There is one. There are some examples, and a very famous instruction set architecture, which is not virtualizable, is the Intel architecture. So Intel never intended to make their instruction set virtualizable. So the Intel architecture, the 32-bit, but the same applies for the 4-bit instruction set, has several critical instructions so that which are sensitive but not privileged. So what do we do with that? There was one very famous solution to that. We will discuss this also in the next session in a more theoretical way. It's called binary transfer. VMware invented that. Or Intel improved their hardware, we'll second, in a way that the Intel architecture was fully virtualized. So what is the main idea? You have the binary, you have the application, like the operating system, the Windows operating system, which should be run or some other code which should be run in a virtual machine. So you scan the whole source binary and just patch or replace problematic instruction. Sounds simple. It wasn't that simple. I can tell that's why VMware was, for a long time, the only successful company in the field providing a proper virtual machine implementation for the Intel architecture. Oh, I have to do this. For the remote lecture watchers, this is the code, 9636. I will repeat at some point. I think I should repeat it at some point. Yes. Yes, sure. Yes. So essentially, this thing happens. So there was a privileged instruction that needed to be handled. And typically, you don't want to patch or like add code into the operating or into the original code, because that is tricky. We will see this also in the next lecture. Why this is tricky, especially for the Intel instruction set. But what you want to do is you want to make this, if this instruction should appear, you want to jump into a special condition or in a special code of the virtual machine monitor, which executes then code as it would have executed on the real hardware, and then goes back. We will discuss this in the next section. We have in the next session a bit more about the binary translation and how this works in general, and the theoretical concepts behind that. To fix this, and to make this a bit more efficient, Intel introduced the VMX technology. There is a technical equivalent implementation by AMD, but we always say this is Intel architecture 2-bit, but this applies this also to implementations which essentially the same. So what they did, I'm not sure if you can see this properly. They added another another CPU mode. So the CPU now has another extra mode. Tells the CPU that it runs in, or it currently executes virtual machine. And this way, Intel couldn't fix the past. So the Intel CPUs are very famous and very popular because they remain compatible with old code and still run pretty much old code on. But they didn't want to break that. So it's usually not a good idea to start complete new. So they applied a different fix. So implemented the VMX root mode. So the behavior is as on previous CPUs, legacy software or old software or software that is not aware of this mode, or operating systems that are not aware of this mode, they run completely correctly this mode. But most importantly, also the virtual machine monitor runs in that. And in the not-root mode, all sensitive instructions or the behavior of the sensitive instructions or semantics of sensitive instructions have been redefined. So Intel just marked all the sensitive instructions. Sensitive instructions happens in VMX not root mode. They will cause a trap to root mode, and this can only happen if a virtual machine monitor runs, because the virtual monitor needs to switch on that mode. So the virtual machine monitor is able to handle this instruction and deal with it. And obviously, all guest OS run in not root. So how this works? So very similar to the previous picture with the time slices, but we have something here, but a hardware context switch, an additional operation is, and make that work. The Intel CPU has additional registers which can capture, can keep the state of a guest running on the CPU. Then it can switch. Keep this. Pointed. So the context switch is like you switch the root mode on and off. You have a VM entry, which results in loading the control registers, and you have a VM exit, which switches from running the guest operating like non-root mode back into. And to make this, and this is why it is fast and why it works pretty well. All the registers and address space is swapped a single operation. So context switch here between two virtual machines, everything happens in one atomic. So what we achieved until now is we virtualized. We can move operational jobs, just compute from one virtual machine another one, or from one physical host another one without letting them notice that. But this is not a computer consists of way more components than just the CPU. So we need to do more. We need to think about other resources virtualized. One is memory, and actually this is as complicated as you, but I will keep it short. So applications typically have a logical view on memory, so they are able to access physical memory. There is already an abstraction layer on that. So the operating system, the real physical memory. So if you had a lecture about the operating systems, you know that there is a page table which translate virtual address of a process into a physical. Now, if you virtualize memory, we need another layer. We don't have, because we have the logical view, we still have the physical memory, but we have something in between, which is the real physical. Previously, the real memory was equivalent with the physical one. Now, if you configure a virtual machine, you have to assign a certain amount of memory to that guest operating system, saying 2 gigabytes. For the guest operating system, this appears as physical memory, the real memory. But in reality, it isn't. It's still somehow virtual. So we need to implement this here for every physical machine, and then the virtual machine monitor has to do another translation of what the virtual machine believes to be physical memory into the real physical. So the Intel architecture does this in hardware because this is a very expensive operation. So you have a page table pointer which points to the page table. So to make this virtualized, we need to virtualize this page table pointer. And as previous, it works the same way as every time someone tries to access this page table, the virtual machine monitor has to take notice and has to point to the right page table, depending on the current state and the current executed virtual machine. So it's pretty much the same idea. Instead of virtualizing and trapping on privileged or sensitive instructions, now we trap if we want to change or if we access a certain register containing the pointer to the page tables where the hardware is actually maintaining, or the operating things that the hardware is maintaining, the relation, the logical addresses. So yeah, if the VM reads or writes this register trap, we trap either automatically because it's already because this is a privileged instruction, or we have patched the code. The VM reads the request. If the VM reads the request, we return the virtual pointer. If the VM writes something, we update the shadow tables. The problem with this this is a very, very expensive option to run multiple machines on multiple virtual machines, same hardware. This is happening a lot. Translation. That's why it was turned into hardware in the first place. So it would be good and similar to the virtual machine extension in hardware. We have a similar extension for memory. So that's what we call standard page tables. And on AMD machines, called nested page tables. And it works in a pretty naive way, or very similar to the way it previously worked. It just do the paging twice in hardware, do the virtual to real, whatever the guest thinks real, and then on the virtual machine does another one, converts the real address to a real fit. And this is happening in hardware. The speed up is significant. Intel claims first version. I don't have any pictures. I guess they improved a lot. The first version improved by 20%, which is a lot, just with this single hardware extension added. But these, even though these seem to be complicated, of CPU memory, the real difficult part are I/O devices. So one problem is it's a huge number, plenty of them. One very popular class of I/O devices which gained a lot of popularity in compute community are GPUs, but that's not the only one. The problem is there is no such thing as a unified ISA for CPUs. We don't have a lot of CPU vendors as well. Or we have 5, so people can adapt. But we have a lot of hardware vendors. Everyone does its own way of implementing things. Each device is controlled in a very specific way. And deal with this problem, operating systems or the operating system programmers said, we'll implement a few, and the rest is on you. So if you do a new super hardware, well, you have to provide driver for it. Fair enough. If you want to virtualize this, like a vector where we can intercept, we could provide a virtual version of the device. That's a cheap one, but also an expensive one. Twice. We can intercept virtual machine requests made the virtual device and convert the request and perform the action. But this is actually essentially more or less rewriting the driver, doing the same job that the driver does on the operating system level, and that has been done typically by the engineer implementing or developing the hardware. Now it has to be done on the virtual machine. Not a very good idea. So, but we need to take a closer look what is actually in scope of virtualization of I/O hardware. So we have dedicated devices. So they're dedicated to a single guest. That's typically a display. Display is difficult to share. A mouse, a keyboard, they usually do not require to be virtualized. If you need to use this with a virtual machine, you typically bypass or pass through the control from the VM directly to the device. So the keyboard controller can, not really, but you can imagine, can directly interact with the VMware. So in practice, virtual machine monitor support is required because someone has to handle the hardware interrupts, but it's doable. So you can pass through. We can have partition devices, so we allocate certain I/O devices or certain parts specifically to a certain CPU. So if you have a GPU with, I don't know, 2 cores, you can dedicate 1 core exclusively to one virtual machine and dedicate the other core to exclusively to the other machine. That's also not that hard. But then we have shared devices, very popular, the network adapter, also popular interfaces between storage devices, like disks and the virtual machine. That is way more difficult because each VM has its own virtualized state of the device. Say for the network adapter, every machine has its own IP address and also its own MAC address, because otherwise the network wouldn't work properly. The same is for the virtual disk. The disk has a state, so it's reading, it's busy. You send a number of requests and wait that the request will be executed and so on. So the machine has a state. So everything has to go through the virtual machine monitor, and that's not very efficient. So if we think about, especially about network and storage, if you want to have a virtual machine, you want a gigabit connection, because otherwise computational science won't make sense. The same applies for storage. You want to have a decent throughput. So this is another way of looking at it. You have the application. Previously, the application issued system calls like read something from the disk or write something to the disk, do network I/O or whatever. The operating system had drivers. The drivers translated the abstract operation to a concrete one, and the driver operated the hardware appropriately. And the virtual machine monitor does that, for instance, for memory or for other things. But in general, to abstract this here, especially with the I/O drivers, it's a much harder task. There are also some hardware related things, but it's a much harder task. So with virtualization, part of the I/O operation is carried out by the guest operating system. Another part is carried out by the virtual machine monitor. And the first point is important and difficult because it's not visible, or parts of that are not visible to the lower layers. The virtual machine monitor can intercept such I/O requests and convert it to a virtual device operation, but that's expensive. And the other question is, where is the appropriate layer to intercept that? Is it, if we go back here on the system call layer, or is it here with the drivers, or is it on the physical layer interacting with the hardware? There are some solutions to that. Memory mapped I/O. There is there are extensions now by Intel and by AMD to virtualize also this. Otherwise, the virtual machine monitor wouldn't even know that the guest operating system is operating hardware, because it would just reading and writing memory. So the other way is to intercept on the driver level. That is what you typically have today in virtual machines. So what we call the VirtIO. So you add or you implement a guest in the guest system, a very specific driver, which is not operating the real hardware, but it actually operates the virtual machine monitor, and only has a very thin layer, so it's highly efficient, and is able then to use the host hardware in a very efficient way. So you see, in practice, this is the popular and actually the doable approach. However, to summarize where we started and where we came from, we wanted to make a computer system, portable as possible. By abstracting physical hardware, by the means of virtualization, we can make the lab infrastructure portable. So it's not tied anymore to the hardware you have in the lab. So the VMs, virtual machines, became portable to a certain degree, but the code still depends on certain CPU features. So we had this, if you run scientific software and compile the code with a very fancy new Intel compiler, the compiler is able to optimize and to use new CPU features which are only available in the new generations of Intel CPUs, AVX 512 or something like that. If you move this then to another architecture, like from AMD or an older generation of the Intel architecture, your code won't execute. It will break. The virtualization still depends on a certain degree on CPU and hardware features. To make virtualization actually happen, Intel and other vendors, well, fixed to a certain degree their hardware and added features to make that possible and to make that efficient. which is super cool for the cloud users, because the cloud is fast and the cloud works. But our intention is we want to look in the longer perspective, at the longer perspective. So we still depend very, very much, even though we abstracted very much away from the hardware, we still very, very much depend on CPU and hardware features. And the virtualization of I/O devices remain very, very difficult, especially in terms of portability. If you have a VM that contains VirtIO drivers, these VirtIO drivers, they need a complement on the host system or on the virtual machine monitor. So these drivers won't work if you switch the virtual machine monitor, say from VMware to some other vendor, or possibly if you switch from one cloud provider to the other cloud provider, because Amazon fixed the Linux kernel on their instances to do things in a certain way, very fast, very efficient. If you switch the cloud provider, you have to adapt the virtual machine. So you have to reconfigure, or you have to use a different kernel, or you have to use different drivers. So that's still not very optimal. Because most of the development work for the abstraction and for the portability of computers was focused yet on performance only, or mostly on performance, because that was the biggest concern. So otherwise, the cloud wouldn't be that successful as it is today, because it performs quite nicely. But to make use of this in terms of research data management, more work needs to be done. But our approach is to move gradually. So we already did a lot and achieved a lot if all the research platforms would have made that step. So the lab is virtualized in a way, or the experiments or the final product of a research is designed in a way that it is portable and is re-executable on another platform. So, and then the next step is to make sure that this will work in 5 years or in 10 years. So we will talk about this in the next sessions. What would be the next steps, and how we make this even less dependent on special hardware and special configurations, and make this as portable as possible. So this is all for today. I hope also the rain has stopped. The next lecture is on Thursday, same time, and then we will discuss more about the binary translation and emulation, and why virtualization and emulation are actually very closely tied. You already saw in this lecture a bit that we always came back to that certain instructions need to be rewritten, that we need to do binary translation and so on. And especially when it comes to I/O devices, emulation is one way to deal with this problem. So thank you very much. Have a nice evening.